let us illustrate the method of variation of parameter in case of finding particular integral of a differential equation of the form this. In our capacity, let us concentrate on second order differential equation only. Now we know that this differential equation has the general solution written as y general written as y complementary function plus y particular integral. Okay, where we get this YCF as the solution of f dy equal to 0 and yp as 1 upon fd operated on fx. This we know, standard. We have standard procedures of finding this particular integral whenever this function is e to the power x, or this function is cos x sin x, or this function is any polynomial in x. In all those cases we have specific tricks to find the particular integral, but variation of parameter is another method of finding the particular integral from this complementary function. We know that since we have assumed that this is a second order differential equation, so you know we have two complementary functions, isn't it so? We have two complementary functions. One is say y1 and another is say y2. They are the two complementary functions, two CFs of this differential equation. Then to find yp of 1, we assume that yp of 1 may be written as u1 y1 plus u2 y2, where u1 and u2 are two parameters of x, such that we impose a condition on this u1 and u2. What is the condition? Condition is that the derivative of u1 prime into u1 plus the derivative of u2 prime into y2 is equal to 0. These u1 and u2 are parameters of x. Okay, function of x. Okay, so with this concept, let us move on to find how we can find this u1 and u2 and ultimately this yp whenever we know y1 and y2 as the two complementary functions of this differential equation 1. Okay, so let us move on to illustrate this. See, we have taken yp as u1 y1 plus u2 y2, and you should remember let us take a specific form of the second order differential equation. Let us take the form as d square plus say ad plus b operated on y is equal to fx. This is the specific form of our differential equation, where a and b are obviously some constants or some functions of x. Okay, so since y1 and y2 are the complementary functions of this equation 1, so we must have d square y1 plusady1 plus by1 equal to 0, as well as d2y2 plus a dy2 plus by2 equal to 0, since y1 and y2 are complementary function of 1. Since we know that what is the definition of complementary function, this is the solution of d2 plus ad plus b operator on y equal to 0, and we have assumed that y1 y2 are the complementary function, so they both will be 0, and we have taken the particular integral yp such that u1 prime y1 plus u2 prime y2 is equal to 0. This is a condition we have imposed. Now let us see that what is dyp and what is d2yp. See that if we find dyp and if we use prime as derivative, so dyp becomes u1 y1 prime plus u2 y2 prime. Simple. Since u1 prime y1 and u2 prime y2 is 0, and what is d2yp? It is the derivative of this, and it becomes u1 y1 double prime plus u1 prime plus u2 y2 double prime plus u2 prime y2 prime, when prime denotes derivative with respect to x. Obviously we know that this is a product function, and we have two terms from this, when u1 is kept constant, when y1 is taken derivative of, and then when y1 prime is taken constant and we take the derivative of u1, so it becomes u1 prime y1 prime, and similarly here u2 prime y2 prime and u2 y2 double prime. So this is d2yp and this is dyp. Just plug these values here. That is the original equation 1. Now what is the original equation 1? Let us write it here. Let us write it here. If we assume that yp is a solution of 1, then we must have d2yp plus adyp plus byp is equal to fx. Isn't it so? Now what is d2yp? It is nothing but u1 y1 double prime plus u1 prime y1 prime plus u2 y2 double prime plus u2 prime y2 prime plus what is dyp is this, so it is multiplied with a, and what we get is a u1 y1 prime plus a u2 y2 prime, and byp gives b u1 y1 plus b u2 y2, and that is equal to fx. So we have this type of relation using these two. If yp is a solution of 1, we get this relation. Now just note that if we take u1 common from this one, then from this one, and then from this one, I have taken u1 common, then we are left with y1 double prime. From here we have a y1 prime, and from here we have by1. Similarly, if we plug out u2 from here, here and here, we have u2 into y2 double prime plus a y2 prime plus by2, and we are left with these two terms only, isn't it so? u1 prime y1 prime plus u2 prime y2 prime, which gives fx. And since we have assumed that y1 and y2 are complementary function of this equation 1, we have these two equal to 0, because they satisfy this homogeneous form when we assume this to be 0. right hand side to be 0, y1 and y2 satisfy this equation. So this equation is actually equivalent to only u1 prime y1 prime plus u2 prime y2 prime equal to fx. Simply we have u1 prime y1 prime plus u2 prime y2 prime is equal to fx. And since we further assumed earlier that this is the condition u1, u2 and y1, y2 satisfies, so you can easily replace u2 prime by minus u1 prime y1 by y2. So this becomes u1 prime y1 prime minus u2 prime is replaced by minus u1 prime y1 by y2 into y2 prime. Isn't it so? Simple. And from this we get u1 prime to be y2 fx by, what is here, y1 prime y2 minus y2 prime y1. Isn't it so? y2 y1 prime minus y1 y2 prime. So this is y1 prime. What is y1 prime? u1 prime. u1 prime is nothing but du1 dx. So obviously what is u1? u1 is nothing but, and our target was to find this u1 only, and whenever you have u1 you can easily find u2 from the relation u2 prime is equal to minus u1 prime y1 prime by y2. And a very important thing to note here is that the condition for this u1 to exist is that this term in the denominator cannot be 0, and we say that this is the Wronskian of the solution. There is a terminology, Wronskian of Wronskian, W-R-O-N-S-K-I-A-N. Possibly he is a Polish mathematician who gives us this formula that y1, y2 and y1 prime, y2 prime determinant gives us the Wronskian of these two complementary functions, and this is coming out to be this, and this should not be 0. And whenever we have two linearly independent solutions y1, y2, we generally don't have this equal to 0. So this is the method of finding the particular integral, which is known as method of variation of parameter. Okay, and we can easily apply this to a simple problem. Let us illustrate it with this problem. Let us take the problem of d2y dx2 plus 2 dy dx plus y is equal to 4 e to the power minus x log x. Here obviously d2y plus 2 dy plus y equal to 0 gives the 2 CF or complementary function as what? We have e to the power minus x and x e to the power minus x. Why? Because if we substitute y equal to e to the power mx, here we have auxiliary equation turning out to be m square plus 2m plus 1 equal to 0, and which gives the repeated root minus 1. That means e to the power minus x is a double root, and we take obviously yc as this. This we know, isn't it so? So using this concept, we move on to write the since the complementary functions are e to the power minus x and x e to the power minus x. So to solve this equation with the method of variation of parameter, we write yp as u e to the power minus x plus vx e to the power minus x. Isn't it so? Such that what we have in the theory, this is y1 and this is y2, isn't it so? So we have u prime plus x v prime e to the power